Right, when we study motion, there are some useful equations that we can use to analyze the motion, and these equations are known as the equations of motion. And one of the key things to remember is that when we want to use these equations of motion, they apply to situations where the acceleration is uniform, or another word we could say is constant. Now, there are 5 different symbols, most of which you are familiar with. So we've got A for acceleration. We've got S for displacement, but what you'll often find in a particular problem, rather than them using the word displacement, you might find that the term distance is used instead. So there are places where we really don't have to draw a distinction between the scalar and the vector quantity, and that's where you'll find the word distance often used. But S is the symbol. Obviously, T is time. V is velocity, but we've got 2 symbols for velocity. If we're talking about something accelerating, at the start of the time interval, there will be an initial velocity. So we use the symbol U for the initial velocity. And after the object has undergone the acceleration, after whatever time we're talking about, then V specifically refers to the final velocity. All right, so 5 different quantities that are then used in these equations of motion. Hold it, sorry, I should go back there. I need to go further down the page. What's going on here? Apologies for that. There we are there. Right. See if we can get back to that. We lose them down the bottom of the page. It's a bit of a pain. Go back again. We'll have to just work in this form here. Right, these are the 4 equations. The first one, number 1, V equals U plus AT. Just notice that there are 4 symbols used, V, U, A, and T. There is no mention of S in this particular equation, so you don't have to worry about displacement or distance in that equation. That's the first one. The second equation effectively is distance or displacement equals average velocity. So we've got the average of the initial and the final divided by, divide by 2 to get the average and multiply that by t. So that's our second equation of motion. Now the derivation, in other words, where these equations come from, I'm going to give you out in class a sheet of paper that shows how we work out these equations. Here I'm just quoting them and I want you to use them. All right, S equals ut plus 1/2 at squared, and the final one, v squared equals u squared plus 2as. So that's equation 3, if you like. That's equation 4. And just reminding ourselves then, I said the first one didn't have s in it. The second one does not have acceleration in it. The third one does not have final velocity in it, and the fourth one does not have time. So it just depends what information you're given in a problem and what you're being asked to find as to which of those 4 equations you may choose to use. So note those 4 equations down, and we're going to have a look now at an example of using those equations, and I'll work through the example on the board here. All right. A car moving initially at 3.5 meters per second accelerates at 2 meters per second squared for 5 seconds. Now, I would suggest to you that one of the key problem-solving techniques in using these equations is to extract from the problem the information provided. Write down the various quantities with the symbol. So a car moving initially, so that is U, equals 3.5 meters per second. Now I'm saying to do this, I'm suggesting you do this. I can guarantee that every year some students do not listen and they want to do their own thing. They think, oh no, too easy. And there'll come a point when we get into more complex problems where you will muck it up because you do not sort of use this type of approach. All right, what else we're given? Acceleration equals 2.0 meters per second squared. And we're given the time, t equals 5.0 seconds. Now let's make this part A that we're doing here, and we'll do probably part B and C on another page. All right, and what are we being asked to find in part A? We're being asked to find V. Now, if you write down those four things there, you then look at them and say, okay, which of the equations of motion from the previous page would I choose to use? There is no mention of S, distance or displacement here. So you choose the equation that's got these four terms in it, V, U, A, and T. All right, and so this one's, I'd say it's the first equation that we're choosing to use, V equals U plus AT. So writing those four things down helps us to identify which equation to use. All right, once we've done that, 3.5 plus 2.0 times 5. I'm putting the 0.0 in, that's just sig figs that we're thinking about there. All right, so it's 3.5 plus 10 equals 13.5 meters per second. All right, so that's the first part. All right, part B. How far does the car travel while it is accelerating? So let's, as I say, start up a new page here just to give us a bit of room to work. And let's go full page perhaps, if I can remember the numbers from the problem. All right, so part B. How far? So we're being asked to calculate S. What did we know? We knew that U was 3.5 meters per second. We had that acceleration, I think it was 2.0, wasn't it? Meters per second squared. T was 5.0 seconds. So we could look for a formula that relates those four things together. S equals U T plus 1/2 A T squared. All right, so 3.5 times 5.0 plus 1/2 of 3.5 times, what am I doing? Sorry, half of 2, apologies. Get it right, 1/2 of 2.0, the acceleration, times the time 5.0 squared. Right, 5 times 3.5, what's that, 15, 17.5, plus 1 times 5 squared, 25. So what do we get? That's what, 42.5. Now that's not the only way of solving this problem. Once you get partway through a problem and get some numbers to work with, there are other ways of doing it as well. Remember, we had worked out the final velocity to be, what was it now? Trying to think back, 13.5 was it? Let me just go back and check. Final velocity was 13.5 meters per second. Yep, sorry. Okay, so we've also got that piece of information. So we could have used S equals U plus V over 2, that's average velocity times time, to work out the distance traveled. And this is probably, in fact, an easier calculation to do. So 3.5 plus 13.5 divided by 2, that's the average of those two velocities, times 5.0. 3.5 and 13.5 is 17. 17 divided by 2, 8.5 times 5.0. And if you work out 8.5 times 5, 8 5s are 40, and a half of 5, 2.5, equals 42.5 meters. All right, and you probably, if you really wanted to, even could have used V squared equals U squared plus 2AS, except that would be a bit messier because the thing you're trying to find is locked in the middle of the equation. All right, so that's the second problem there. Let's create another page just to do the third part. And this one we're interested in the distance traveled in the third second. So people get a little bit confused about what is the third second. The first second goes from t equals 0 to t equals 1. The second from t equals 1 to t equals 2. So the third second goes from t equals 2 seconds to t equals 3 seconds. All right, now what things apply to the whole motion? We definitely have got the acceleration, that's not changing throughout the motion. The time taken to travel that 1 second would just be 1 second from t equals 2 to t equals 1. What else do we know? We're trying to find S. AS, do we know V? Do we know U? Well, if you wanted to, one way of solving this would be at t equals 2 seconds, let's figure out the velocity. V equals U plus AT. We started off at 3.5 plus 2.0 times 5, so that's 10. Sorry. 2.0 is the acceleration times 2 seconds. So that's for 7.5 meters per second. At t equals 3 seconds, the velocity would be u plus at again. But now the initial velocity would be what you started with after 2 seconds. So it would be 7.5 plus 2.0 times, hold on, sorry, apologies. If we're trying to find the velocity from the beginning after t equals 3 seconds, yeah, we would go back to using the initial velocity plus acceleration times 3 seconds. So that's going to be 9.5. And then from there, you could use S equals U plus V over 2 times T. So 7.5 plus 9.5 divided by 2. And the time that it's doing the accelerating for now is this 1 second interval, just in the third second. So what we've got here is the velocity at the beginning of the third second, the velocity at the end of the third second. And we're taking the average of the two and multiplying by 1 second, being the time interval between t equals 2 and t equals 3. So we've got 9.5, 10, 17 over 2, which is going to be 8.5 meters. There are other ways of doing things. If we think about it in terms of just a graph, plot a graph of velocity against time, we've got a line like that. We've got our starting velocity of 3.5. We've got our finishing velocity up here of 13.5 meters per second. There's our t equals 2. There's our t equals 3. What we are effectively doing in terms of the graph is we're working out that area there, the distance traveled in the third second. Okay, this should equip you with enough ideas to be able then to cope with the questions in the first of the worksheets, which we'll get onto in class.